Even if it could be built, there's a larger question. Would it be worth the effort? Could such a vast undertaking ever justify its huge cost? The answers to those questions depend on one thing: speed. Unimaginable speed. Up until this century, the fastest way across the Atlantic was by ship. A one-way trip took about a week. Planes, and later jets, brought the trip down to hours. Today, the fastest way is the supersonic jet called the Concorde, which makes the trip in about 3 hours. But the Concorde is so expensive, only a few can afford to fly it. Could a train go faster than a supersonic jet? One thing is certain: there could be no diesel trains in the tunnel. There would be no way to vent the deadly exhaust. The only possibility would be an electric train. A very fast electric train. Today's fastest trains run between Tokyo and Hiroshima in Japan. They're known as the bullet trains. These sleek state-of-the-art trains will approach top speeds of 250 miles per hour. Not bad, but nowhere near fast enough. To make the transatlantic tunnel feasible, designers would need to build a train that went 20 times faster than today's fastest working trains. And as incredible as that seems, it's theoretically possible. The main limit to the speed of a train is friction, caused by their weight on the tracks. But what if that friction could be reduced or eliminated? Here in Germany, engineers are testing an experimental train that all but eliminates track friction. Because the train doesn't ride on tracks. This train literally floats on a magnetic field. It's called maglev, for magnetic levitation.
Maglev technology is doing what a typical train does, except using electromagnets. Instead of having wheels and rails, we have magnets to lift and guide the vehicle, and then a non-contact propulsion system to propel the vehicle down the track.
With a powerful enough magnet, literally anything on Earth will levitate. A drop of water, an ice cube, even a strawberry. Maglev trains work like this. When the system is first powered on, a powerful electromagnetic field lifts the train up about an inch off the track. Powerful generators in the track then begin to produce waves of magnetic energy, which propel the train forward. Because the train never makes physical contact with the guideway, there's no friction. And that makes the train very fast. The current model is designed to go as fast as 310 miles per hour, but the technology can potentially go much faster.
In theory, there are no limits to how fast a maglev system can actually go. There are obviously practical limits. There are also economic limits. But the technology itself is capable of much higher speeds.
Maglev technology holds the greatest promise for a transatlantic train system that might someday hurtle through an undersea tunnel at the speed of a rocket. But in order to reach 5,000 miles per hour, another problem would have to be solved. The primary force that limits the speed of all moving objects: air resistance.
The faster you go, the more air resistance you have, which means the more power you use. And so if you can do away with that air resistance by putting the train in a vacuum, then obviously you could go at much higher speeds with the same amount of power that we're currently doing today for 200 miles an hour or 300 miles an hour.
The transatlantic tunnel would need to be totally airless. A perfect vacuum. Vacuum tubes are nothing new. The technology was developed a century ago to send documents and small parts through factories and offices. The concept is simple. Pumping all the air out of a tube creates a vacuum. With no air, there's no air resistance to any object going through it. Give the object a shove and it goes into the equivalent of instant freefall. It's literally sucked through the tube. Could engineers turn the transatlantic tunnel into a vacuum tube? Engineers at MIT are experimenting with a working scale model to find out. A miniature maglev train is placed in a tube that represents the transatlantic tunnel. Smoke is added to show the presence of air. The train slides slowly. Next, all the air is removed with a vacuum pump. Now, when the train is added, its speed is tripled. Without air to push it back, the train slides completely unimpeded through the tube. Of course, removing the air from a 6-foot tube is one thing. Turning a 3,000-mile-long train tunnel into a vacuum is quite another matter.
To initially pump all the air out of the transatlantic tunnel in order to create the vacuum necessary for high-speed travel, we require several months of pumping at millions and millions of cubic feet per hour of pumping speed.
It would take the pumping force of about 100 jumbo jet engines running continuously at full throttle for about 2 weeks. But even assuming the magnetic power and vacuum technology all fall into line, engineers would face another potentially crippling problem. The deadly force of acceleration. How could the human body tolerate the crushing G-forces that would almost certainly occur at those speeds? When an object, space shuttle, jet plane, or train accelerates or changes speeds, its occupants will experience either a sense of increased weight or a sense of lightness. These are G-forces. Up to 3 Gs, or 3 times the normal pull of gravity, as the rocket accelerates from 0 to 17,000 miles an hour in about 8 minutes. Of course, once they reach orbit, they feel no G-forces at all. Even though they're traveling at 17,000 miles an hour, they are not accelerating, so there are no G-forces. This fighter pilot is undergoing 9 Gs during a simulated dive,
4 Gs,
making him feel like he weighs 1,500 pounds.
burnout 6 Gs,
The blood stops flowing to his brain, and he momentarily blacks out. If the transatlantic tunnel train accelerated at the rate of a space shuttle, the G-forces would turn it into a tunnel of torture. If the passengers aboard a transatlantic train had to endure those kinds of forces, there'd be plenty of seats available. Fortunately, that won't happen. The key to comfort would be a controlled, gradual acceleration.